Okay, welcome. It's another week, right? No, it's Monday. It's not Tuesday yet. It's still Monday. All right. For those of you who are interested, I brought the cable for the TI-84 calculator. If you want the program Riemann sums, which will basically do most of the homework 12.2 for you. So it's a good thing to have. But we'll push forward to get done a little bit early, so we have the last part of class and just come up. It takes 5 seconds. Probably takes me longer to get you hooked up, but 5 to 10 seconds, we'll put it that way. Just a few updates. I did update the homework scores, and I went all the way up to, I think, 13.3, which is what we've covered. A lot of you have not started those. Don't worry about the zeros. Again, with the homework, I will continually update all the way back to the beginning. The early homeworks, I believe they're extended to the end of class. The extra credit 12.6 section, that's extended till December 8th, so you have till then to work on it. December 8th is the day after the exam, so even after the final exam, you could do that. I will update scores after I get the grades for the exams. Also, I posted, we have the location of where our exam will be. You'll be taking it with my morning class, so we'll have 187 of us all in one big room. LSE, I haven't ever been there, but I'll probably go check it out. I put a little map to help you find it. So that's on track, and that's Thursday of finals week, Thursday, December 7th, and it's in the evening. 7:10 to 9. It's just with common finals, that's what we do. So make sure you get things arranged. If you've got something, talk to me as soon as you can about as far as scheduling conflicts, and we might be able to get something worked out. We will get something worked out. We always work something out. Okay. Any questions, concerns, comments, things you've noticed that are different than they're supposed to be? I think I've updated the homework due dates for 12-1, 12-2, or 13-1, 13-2, and 13-3 to be after or about the day of the exam. So you should be able to continue working on those. Sometimes after I do the change, I have to hit a save button. Sometimes I forget to do that. So just let me know. The idea is that you'll have all the way up to the exam to work through everything. Oh, and we are recording. Yeah. Okay, good. We are recording. Okay, so let me go ahead. Start the slideshow. So today actually is nothing as far as skill-wise that is new. What we're going to put together is 13.1, which was finding the antiderivative. You'll see in the homework there's also a few that will require you to use U substitution, which, what was that, 13.2? And then it ties in the concept of the Riemann sums. You won't be asked to do Riemann sums, but remember, Riemann sums was the area under the derivative curve. So we're going to tie all those three things together in what we do today and see that we can actually get something of value out of it. And they've got a real fancy sounding name for it. So what we're getting at is the definite integral. Remember, we were doing an indefinite integral where we always had a plus c. We integrated to something that was close but was missing the constant. We're going to see today we don't need to worry about that constant anymore because we're going to get exact values of the integrated function between 2 points. Let's see, and I think I'm going to do this a little different, where I'm just going to kind of introduce some notation as I do this. We'll work through it, and then the textbook has some slides where they kind of work this from the beginning, and we'll make connections. But I think if we go with what we're doing, I think this will work anyway. Okay, so we've got a problem like this. where we're given the marginal cost. And what is a marginal again? Marginal is a rate. It's the cost for one more. It's a rate of change. It's also a derivative, right? It's all those things. So we know we're going to be given a derivative function, which is pretty much everything on this part of the class, for producing baseball caps at a production level of X caps. And they give us the function here. The other reason we know this is a rate is this word per. So when you see something per something, dollars per cap, that's a rate. It's a derivative, okay? And so when you're given the derivative, we're trying to find what came before the derivative, right? That's really what this part of it is. We give you a derivative. Where did we start? Okay, what was the antiderivative function? Find the total change of cost if production is increased from 100 to 200. So this is kind of a little new, but we're going to see it's sort of a real simple way to apply it. So when we were getting the antiderivative, we used this symbol. Is that showing up? I might have gotten it to, let's make it a little thicker. Okay, so we're going to do the integral 4 minus 0.001 x dx, right? We've done this before. This was from like when we started off, find the antiderivative. Again, we spent a whole day going. We're going to do this. What I'm going to add here, I'll do that in blue, is we're going to add some limits, and so we're going from 100 to 200. So we'll put the 100 here and the 200 there. So it's kind of a new thing we're going to see, and this is what's called a definite integral. We're definitely going between 2 points, and we're going to get an exact value. We could use Riemann sums to get an approximation, but we're going to see we'll do the mathematics we're going to use will give us the exact value. And then we'll use the calculator to show that that's an exact value. Okay, so how do we integrate this function? If we have just a constant, when we integrate it, what does it become? That constant times the variable, right? Because it's like 4x to the 0 power. We're going to add 1 to the exponent, so it's going to become 4x to the first power. So let's do that in maybe green. So this integrates as 4x. And I'm going to emphasize it with the first power there. I'm going to put a little green x to the 0 power there, because x to the 0 power is 1. It's invisible most of the time. So that's how that integrates. So any constant, when it integrates, it becomes that constant times x, so 4x. How do we integrate 0.001x to the first power? First step, we add 1 to the exponent, right? And then we divide by that new exponent. So we're going to get minus 0.001, it comes along for the ride, x to the second power, all divided by 2. And again, usually what we're doing, we would put plus a constant, but we're not going to do that anymore, and you'll see, and they'll explain it in a couple steps, but we don't need to do that anymore. So we've done that, but instead of plus a constant, what we're going to do is we're going to include this part, the boundaries, on here, saying that we want this to go between 100 and 200. Okay, so we, in place of the c, we've got this exact, this is telling us we've got a definite integral, we're going to get it. Okay, so let's just kind of clean that up a bit, and then what we'll see is the way we get this, we plug in the 200 to the function, and then we subtract the 100. So, because what this is saying is starting at 100, what's the cost to get to 200? So the cost between 100 to 200. So wouldn't that make sense that you would figure out what 100 is, subtract it off, because that's now the starting value at 200. Because typically, if you, once we, now remember, is this function a derivative? No, not, it's an antiderivative. It's the function that gives us the total amount. So when we plug 200 in here, it's giving us the cost of producing 200 total items. So if we subtract off the cost of producing 100, we get the cost between 100 to 200. Does that kind of make sense? And we'll go through it a couple times, and maybe in times it'll make more and more sense. Okay, so once we have this, this is our function with the capital F, right? This is the function that existed before the derivative. If you took its derivative, we'd get back to what we started with. I'm going to clean this up a little bit. 0.001 divided by 2 is going to be 0.0005. So think of this as sort of 10 divided by 2 is 5. So what we're going to do is, let's change colors again. So this is sort of our answer function. We're going to take 400, plugging in 200, minus 0.0005, 200 squared. So that's the first. So I just took that function, plugged in 200. That's all I've done. What I'm going to do next, because that would give me the value or the cost, because this is a cost function, right? It would give me the cost of producing 200 caps. That's what that will give me. But I don't want that. I want the cost from 100 to 200. So what I do is I subtract off, and I'll put a big parentheses, 4 times 100 minus 0.0005 100 squared. And if it doesn't make a lot of sense, I'll be honest. I woke up this morning. I've been doing this for probably close to 40 years. I just started to understand it this morning when I thought about it. I mean, I could do it, but I said, I don't know quite why it works. And then for some reason it just clicked, because the way they were explaining it. So this is the area under the curve of this function, or it's the integrated function at the end point minus the starting point. Okay, so let's calculate that. The first one, bless you, 4 times 200 minus 0.0005 times 200 squared. I plug in that, I get 780. And I'll do the back part here. I'll do 4 times 100. And if someone could try this out too, just to make sure I get the right numbers, because if I plug in, if I forget like a 0, so I got 0005, and then 100 squared. On the second part, I got 395. And notice how when we're doing this, we're going to get numbers, so we don't have to worry about doing too much algebra with this. We could have even left it as 0.001 divided by 2. We're going to calculate. And so what's our answer? Our answer is 780 minus 395, 385. And let me put the units on here. They didn't really say we had to. What's that? It's dollars. It's not dollars per cap, because it's no longer a rate, it's an amount. It's a cost. It's a total cost for producing those hats. For producing 100 caps, specifically the caps from 100 to 200. And again, when we're running a business, the first 100 might have cost more, right? This is the second 100 that was produced. So that's what we're getting here. And notice, nothing skill-wise, anything new. We talked about doing this, the integration. The only thing is we're putting now, since we have some boundary points, we put it in. This is similar. Watch this with the, let's see, how do I don't want to stop. Let me, I want to get out of this. No. Here we go. We're going to keep that. I want to use my graphing, my TI-84 calculator. Probably make me sign in, but we'll take a little pause. And this is basically the lesson. The rest of the stuff is going to convince you that this works a bit. It'll come back and introduce this notation, but if you followed along with it, if it made sense, I think maybe it should, just put your boundaries here, integrate it, put the top one in, put the bottom. That's how I got through it. I said, that's pretty simple. I don't need to understand this stuff. I know how to do it. And so for years, that's what I did. Okay. I think I used this one. Okay. So remember, what we're going to put in here to get the area under the curve, we're going to put in the derivative function. And what we're going to see is the area under the derivative function, the rate function from 100 to 200 is $385. Okay, which is kind of cool. Oops. Oh, I probably shouldn't have closed that. No. Close. Okay. I think if I leave that open, I should be able to get into that. Okay. I'm wondering maybe try this one more. Maybe I used a different Google account. It says I signed in. Maybe I used my personal. Signed in with an extra. Well, okay, I think it's coming. There we go. Okay, so I'm going to put in the derivative function, which was 4 minus 0.0001 x. Then I'm going to delete this, delete this, delete that. So that was the derivative function, right? I don't even have to integrate it. I'm going to graph it, but remember, they want us to go from 100 to 200. So those are x values. I'm going to change my window so that it at least covers that. I'm going to go from -10, let's go to 250, so we can see sort of a little bit on both sides. The Y values, I'm not quite sure. 10 might work. I know it's 4 minus 0.001x, so going probably 4 is about as high as it needs to go. Graph it, let's see what we see. So my line is all messed up here, but so it's almost like a straight line at y equals 4 because it's subtracting just a little bit. So now I can use my calculator tools, second calc. Remember the calculator, this is sort of like an exact Riemann sum. Number 7, the integral of our function. Go there, go hit enter. First thing it asks for the lower limit, that's the 100. Enter. And then it wants the upper limit. I put in 200, and it will get the area under the curve from 100 to 200. It says it's 398.5. I had 385. Did I miss something? 4 minus 0.00. Oh, maybe I got one extra zero, I think. Right? Oh yeah, I put in an extra zero. It's 0.001. I have an extra zero in there. I have 3 zeros and there should only be 2 zeros, so let me delete one of them. Now we'll get exactly the same answer we came up with. So it's a little bit different. We'll go second calc, number 7, which is integration. And again, now we enter our lower limit. We enter our upper limit. We see and now it's 385. It's exactly what we came up with the other one. Okay. On the homework, all you got to do is enter in the 385. So you could use the technology first. I still encourage you to kind of go through the process of integration and seeing that you'll get the same answer. But no, we can use our technology now to check our answers, or to get our answers and we check it with our backup. So we've got 2 ways to go about this. Okay. And what we just did is called the fundamental theorem of calculus. Should be music playing right now and angels dropping from the heavens or something. This is actually a very big deal. And I took some of the theorems and stuff out of there, at least if you're a math person, it's a big deal. If you're a business person, it's, oh, okay, gives me my answers, okay. So this is what we're doing, that the area under the derivative curve, the rate curve, is the same thing that you get when you have the original function, the cost function, and you get it, okay. And what you're going to see is that we're almost to the end of our topics, because the next section is the area between two curves, which we just have, because this is the area between the curve and the x-axis. So we add a little bit more, and we've got all our stuff, but we've really got all the skill-based stuff down for this section. Okay, so let's go back to our slideshow. And so on the first slide, I've kind of introduced everything that's going to be new today. We're going to be given a derivative, we're going to integrate it, we can use the boundaries, plug it in that integrated function, the bigger endpoint minus the smaller endpoint, and we've got the area under the curve. Or we could just graph the derivative and use it, get the area under the curve. So this is the book's talk, so this is the book going through everything I just did. So I'll just highlight a few things. So the first method is to basically recognize that we have a derivative and then to take its integral. Now notice they are using the indefinite integral because they're putting the plus a constant. Okay, just like we did before, what they're doing with that is they want to show you that when we go to get this, the constant's going to cancel out, right? Because you'd have plus some constant minus that same constant, so plus and minus, they become 0. So that's why we don't worry about the constant. But notice we've got the same function that we came up with. This one here, 4x minus 0.0005x squared. We got that. We didn't put plus the constant because in the end we're not going to need it. They plugged in the cost at 100. They did that first, and they got the 395. We go to the next slide. They plugged in the cost at 200, and they got the 780, same thing we got, right? But they've got this plus a constant because, again, they're tying back directly to 12.1. And then when they take the 200, the value at 200 minus the value at 100, K minus K is 0. So it's gone. So I just said, don't worry about the constant anymore. They're just trying to prove that that's why you don't have to worry about it. Okay? And notice they came up with the same value we did, 385. Make sense? Okay, and a little bit nicer writing and not all over the place. And again, this is they're getting in that the constant of integration simply canceled out. Okay, that's what I told you. That's what would happen. So we just took this function value, we plugged in the 200, we plugged in the 100, and subtract the two values. That's all we have to do. Okay, just like we did on that first slide. So if you're a person who says, just show me what to do and I'll do it, that first slide showed everything. The rest of this will show you why, or that it works. Method 2, this is what we did with Riemann sums, is to get the area under the marginal cost function curve. And again, since the most accurate way to do that is not with Riemann sums, because you have to take them in small, small, is to actually use a tool like we have in the TI-84 that will actually do that for us. It'll get us the area under the curve. We did that as well. And so they show this as an example. They would graph the original function, 4 minus 0.001x, which is almost a straight line going from 100 to 200, and they could calculate the area under the curve, again, either using Riemann sums, a lot of small rectangles, or a tool that did it. So two ways to do this, okay? When you do the homework, you have two ways to do this, and I encourage you to do both. If you want to go through quickly and use the calculator, get all the answers in and get done, that's fine. But do take some time to practice and go back, because it'll be helpful. It'll be helpful. Okay. And now again, the rest of this is just introducing the notation. Remember this, the little f of x, that is a derivative. The function with the big F, these are the antiderivatives, or the thing that we, in the early part of the class, we were given that and we were asked to take the derivative. It's the total, it's the function that gives us the values, the total values, right? These are the antiderivatives. Okay. And notice the top limit minus the bottom limit. So that's all the notation. Again, I just showed it to you. This is what we're going to do. So if you see, you'll be given a limit, a lower limit and an upper limit. You put them on the integration, and then usually we integrate, so we get some function f of x, and we write it like this from a to b, and then we go to this part here. And then we can calculate. We get a number for our answer. And remember, that number is not a rate. It is an amount, because we integrated. First part of the class, we were always interested in rates. The second part of the class, we are given rates, functions, and now we're interested in totals. Okay. Think about it. When we get to the next lesson, what we're going to do is you'll see this. If you want to know your profit, what do? You take your revenue minus your cost. You're going to see that we can do this with two rate curves. The area between the rate of the revenue and the rate of the cost actually will give us total profit. So again, we're going in circles, but it just depends on what information we're given, we're actually able to get whatever answer we need. If we need the rate, we've got the rate function, we're great. If we've got the original function, we can take its derivative. If we need the amounts, and we were given the rate function, we can go back and get that. So whatever we need, depending on whatever we're given, we can figure it out. And again, this is more, if you're a math major, the proof type stuff, you don't have to prove all this stuff, you just have to be able to do it, use it. So we're going to get to a few examples. And it just talks about when this exists. Well, we're not going to give you a problem where you can't use this and ask you to use it. We just won't. Okay. So, but that's just kind of giving you some more things. So let's get into some examples. Again, we're going to work a few more, and I pulled one directly out of the homework, so we'll actually even get started on the homework. And what time is it? It's 3:30. We'll be done probably in about 15 minutes, so we'll still have a good half hour for anyone who wants to work on homework or anyone who wants the Riemann sum program. We're good to go. Okay, so what we do is we're given now these problems where the integration has limits, a bottom limit and a top limit. Again, we could just go to our graphing calculator. Let's do it backwards this time. I'm going to keep that stuff. Since I've already got it open, it works a lot easier. We put in the function we were given, the derivative function, which was just 2x. Our limits are just going from 0 to 1, so that's an x value. So I'm going to go from -1 to 3. Again, I like to go a little bit bigger so I can see everything that's going on. I don't quite know my y values, so maybe -10 to 10. Maybe it's okay. Let's just take a look. Yeah, it'll be okay. And then we're supposed to go from 0 to 1, right? We want the area. Notice it's kind of a nice little triangle. You could use that. Second calc will come down to number 7. So this is method number 2 that they said we could use, so it's completely legal. Lower limit is 0. Enter. Upper limit is 1. Enter. And it tells us that that area is 1. The area under that curve is 1, so when we integrate it with method 1, we're going to get that answer of 1. We're going to see it's popped out, but that's our answer. The integration, the area under that curve is just 1. And you could think of it as a triangle and base times height and 1/2 base times height. So and it looks like it's got a base of 1, looks like a height of 2. So base times height is 2, divided by 2 is 1. Okay, so you could do it with geometry as well. But let's come back and take a look at doing it with method 2. Method 2 says go ahead and integrate this. So right, this is x to the first power. We add 1. It's going to be 2x squared divided by that new exponent. Right? So we've integrated. We don't put plus a constant. What we do instead is we put this little line and say we're going to go from 0 to 1. Maybe we want to clean it up. 2 divided by 2 is 1. So this is really just x squared. Right? And then to finish the evaluation, we're going to plug in the upper limit, which is 1. So we've got 1 squared. And then we're going to subtract the same function, x squared, at the lower limit, which is 0 squared. 1 squared is 1. 0 squared is 0. Our answer is just 1. Done. So notice we match exactly what we did with the graphing calculator, taking the derivative function and just getting the area under the curve. That tool is very helpful. And I think Casio's also have a similar function, so but definitely this is one of the nice functions of the TI-84 calculator, and it will show you the graph that you're getting the area under the curve. Okay? Questions on that? Does it look really new? Does it look only partially new? A little bit? Okay. So be able to take a derivative or an antiderivative and go. So here's one maybe a little bit more complicated. Integrating from 0 to 1. And this one we'll reverse it. We'll do the method 1, which is the fundamental theorem of calculus. We'll integrate it, put in the limits, get the value, and then we'll check it with our calculator to make sure we get the same values. So far we're doing pretty good, right? So when I integrate, notice there's parentheses here, but if I integrate 1, what am I going to get? 1 times x, which is just x. So this integrates into just x. When I take x or negative x squared and I integrate it, right? Integrating is adding 1. So I'm going to get negative x to the third and then divide by that new exponent. And so that's integrated, right? Each term by term, there's 2 terms. I've integrated both of the terms. I've got the antiderivative. And now all I do is I put this little line, and it tells me to go from 0 to 1. So it tells me to take that answer, that function I've got, plug in 1, get a number, plug in 0, get a number, and subtract those 2 values, and we're done. Okay, so the solution is simply going to be 1 minus 1 cubed over 3. So notice I'm just plugging in 1 to the function. And then I'm going to subtract. This is sometimes where you can make a mistake because you've got 2 terms. If you don't, that subtraction's got to distribute to both of them. But just do the math first, and then you'll have just a single number. That's how I kind of go about this. So we're going to plug in 0 for x and 0 for x here, so we get 0 cubed over 3. It's always nice when they use 0 because a lot of times that's what we end up with is just 0, right? So we have 1 cubed is 1 minus 1/3, minus 0 minus 0, which is 0. And what's 1 minus 1/3? Get common denominators if you want. So 1 I can write as 3/3 minus 1/3 should be 2/3. And if you want 2/3 as a decimal, take 2 divided by 3. You will get 0.6666 going on forever. Eventually it'll round off to 7. That's what your calculator is going to tell you you've got, right? Because the calculator doesn't give you fractions usually. It gives you some kind of decimal. And that's it. That's the homework we're doing. What we're going to do is we'll get out of here. We'll use the calculator. We'll go to y equals. We'll clear this out. We'll just put in the derivative function, right? We don't actually even have to do any calculus on this. 1 minus x squared. So that's the derivative function. We're going from 0 to 1, and so we've already got our window set up pretty good. Going from -1 to 3, that'll include everything. I think this is okay. So we go to our graph. We can see most of what we need to see. I'm going to zoom in a little bit. Let's go from maybe -3 to +3 on the y values. That'll just make it a little nicer. We can see this. And then what do? Technology, second calc, which is a trace button. We come down to number 7. What's the lower limit? 0. What's the upper limit? 1. And notice it fills it in, so we see it. It's the area between the graph and the x-axis. Okay, 0.66667, 2/3, what we came up with. Let me ask you a question. What if we would have went from 0 to 2? What do you think this area? Well, let's do that. Let's. Do you think the number is going to get? Is that we're going to get more area? So you think 0.66 is going to get bigger? Second trace. Had they asked us to go from 0 to 2, we'll go lower limit of 0, upper limit of 2. Ooh, we've got negative 0.666. When the graph goes under, when the curve is under the x-axis, this is considered negative area. So you had positive area minus negative area. So we're going to see that you need to be careful. Sometimes you need to graph it in advance because when we're doing this, if we actually wanted total area, we got to be careful here. And sometimes we do because maybe this is costs became negative or profits become negative. So it just depends on what we're looking at. But when your curve goes under the x-axis, that kind of makes sense. It's the area between the curve and the x-axis upwards is actually negative area. Okay, so just watch for that. There's another problem that will ask you about that. But when you're using the technology, there's positive area and negative area. When we subtract the two, we've actually got, and it looks like there's negative 0.6. There's more area here than there. I think we get like 4/3 of negative area, 2/3 of positive area. When you subtract them, you got negative 2/3. Okay? Questions so far? Is it looking pretty straightforward? And again, it's just getting this pattern. And here's just, they're going to talk you through it. They integrated down here, you got x minus x to the third divided by 3. They put plus a constant. So they're going to go through this a little bit slower than we went. So 1 minus 1/3 minus 0, which is 2/3. Okay. So now we're going to look at one application that we started with Riemann sums. So the definite integral allows us to calculate total change from the rate of change or to calculate area between the graph and the x-axis. So this is what we've been doing. So I don't know if you'll recognize this, but it's the exact same function that we started with when we were talking about Riemann sums. We went to the oil spill thing. And we did it with smaller and smaller rectangles till we got down to, I don't know, about 680 or something. But what we're going to be able to do now is compute the volume released during the first 20 days using the fundamental theorem of calculus. So remember, this function, barrels per day, thousands of barrels per day, is a rate. So if we integrate it from 0 to 20, 0.08 t squared minus 4t plus 60 dt. So that's the derivative function. We're going to integrate term by term, and then we plug in the limits, subtract them. We will get the exact value that we were working towards with the Riemann sums. Okay, so this first one, t squared, when we integrate it, what are we going to get? T to the third divided by 3. Remember, add 1 to the exponent, divide by the new exponent. Negative 4t, that's t to the first power, is going to become negative 4t squared. 1 plus 1 is 2, divided by 2. And that'll simplify a bit, but I like to go through. And then when we get 60, there is no variable here. We could think of this as t to the 0, or just think that 60, the constant, will now become 60t. And instead of putting the constant, or plus a constant, we put from 0 to 20. Okay, so we're going to take this new function, we plug in 20. We can see when we plug in 0, you get nothing, so we really don't have to subtract anything. It's really, since we're going from 0 to 20, we really just need to plug in the 20. Let's simplify this a little. What's 0.08 divided by 3? Well, it's not that pretty of a number, so we'll leave it as it is. We'll go 0.08 20 to the third divided by 3 minus, this cancel. 2 goes into 4 2 times, so this will be 2 times 20 squared plus 60 times 20. And then for the back end, when you plug in 0, it's all 0, so we'll say minus 0, just to remind us that we always subtract the lower limit. When it's 0, typically, in this case, plug in 0, and these are all zeros. Does that make sense? See where that zero's coming? Okay, good. So then we just plug this in our calculator. We're going to get a number. We're done. So 0.08, that's 20 to the third power divided by 3 minus, so you can just enter this in your calculator all along the line, 220 squared plus 60 times 20 . Oops. I think I put a parentheses in the wrong place. So 0.08, let me try this again. I came up with 245, and I know that wasn't right. And I see I put in an extra parenthesis. So times 20 to the third divided by 3 minus 2 times 20 squared plus 60 times 20. Yeah, 613.333. Is that what anyone else got it done? Got that? Okay, good. Always like confirmations. Okay, so when we do this, 613.33333, which is a third, right? Minus 0, but so this is our answer here. And again, when we're doing the Riemann sums, the other thing we can do is we can take the derivative function, which we were given, graph it, and use our graphing tool to get the area under the derivative graph. It'll be the same answer. Okay, so both ways. It's a good way to check if you made a mistake in getting the integral, the antiderivative, or if you put, like me, put in a wrong parenthesis somewhere that maybe you didn't spot. Doing it two ways is nice when you get to a test, because those got to match, and if they match, you're going to feel more confident about your answer. My calculator matches the sort of by hand one I did, or if they don't, oh, I made a mistake. You'll go back and look, and I again, because I knew the answer was around 600 and something, I knew I did something wrong, and what's that extra parentheses in there? Okay, so let's see. Oh, I told you we have enough time, but so this walks it through, and basically does what we did, plugs in all the zeros. So if you wanted to see that, 640 over 3 minus 800 plus 1200. So they've done all this calculation. Did I have a minus? Let's see. Did I get that right? Yeah, I do have the minus. Okay, so now I'm even second guessing. Yeah, 613.3333. Okay, so that's what we came up with. Same method. Okay, so I got one last one, and this one mostly just to kind of set up. It shouldn't be too hard, but you'll get things like this. Calculate the total area of the region described. Do not count area beneath the x-axis as negative. Okay, so that's, you may get ones where there's some that's underneath, but they don't want you to count it as negative, so they want you to count it as positive. You calculate, etc. Bounded by the curve y equals square root of x, the x-axis, and the lines x equals 0 and x equals 25. Okay, so what I want you to see is what they're giving us here is the x boundaries going from 0 to 25. We want the area underneath the curve and the x-axis. That's exactly what we've been doing. And I'm going to show you both ways. So when we take the integral of the square root of x dx and we go from 0 to 25, that's what this is going to give us. Okay. So we integrate x, the square root of x, right? Remember that is x to the 1/2 power. So we add 1 to 1/2, so that's going to give us x to the 3/2 power, right? 1/2 plus 2 over 2 is 3 over 2. And then we have to divide by that new fraction, divided by 3/2. We don't need plus a constant with this one. We just need to go from 0 to 25. And when you divide by a fraction, remember division, you flip and multiply. So if you want to make this look a little prettier, we take the 3/2, the 2 comes in the numerator, the 3 stays in the denominator. This is x to the 3/2 power. And again, we'll go from 0 to 25. Again, the nice thing is when we start at 0, you plug in 0 for x. It doesn't matter what power it's to, it's always 0, right? So we end up with 2, 25 to the 3/2 power divided by 3 minus 2 times 0 to the 3/2 power divided by 3, which is going to be 0. So we just really need this front one. And again, we're pretty much at a place where we're always going to have to use our calculator. Now, you could say, okay, 25, 1/2 power, that's the square root of 25, which is 5. Then you cube it. 5 cubed is 125 times 2, 250 divided by 3. Let's see if I get that right. 250 divided by 3, 83.333. Or just plug it in your calculator, 2 times 25 raised to the 3 divided by 2 power, and that all divided by 3. And I get 83.3333. Okay? And just to show you that it fits the description, if we do the same thing, we're going to keep, oh shoot, oh well, we're almost done. That's the last slide. So we come to y equals, we'll put in the square root of x, and then we just need to have our window going from 0 to 25, so I'll go from -1 to 30. We need to go up a little bit higher. Let's go to 7. We're going to graph it. We're going to go to second calc number 7. Lower boundary is 0. Upper boundary is 25. Fills in the area. It's 83.333, just like we got. And you visually see it. That's the area under the derivative curve from 0 to 25, and it's above the x-axis. Okay, so there's several problems that are similar, like this word problems, where you're set up. They will give you the derivative. Again, you could use your technology to do it. You could use the other by hand, but again, I encourage you to use both, and that will give you 2 ways of checking things, especially when you go into the test. Okay, we don't have much more. The only next lesson is that we're going to have 2 curves, and we want the area between the 2 curves, and it's really just going to build off of what we did today. Nothing too new, just another little thing to the process. Be good? All right. If you want the Riemann sums program, I have it. And again, it won't take too long. If you just want to bring your calculator or call me over. Thank you. Oh, let me stop the recording.